On va pouvoir aborder la session séminaire de cette session. Et donc, notre premier orateur, je vous rappelle qu'il y a un autre séminaire par Shi Weizhang à 2h, en salle 2. Mais notre séminariste maintenant, c'est Tarik Yefsah, qui est au laboratoire Kessler-Bruxelles, où il s'occupe de fermions dans le continu, ce dont il va nous parler aujourd'hui. Et Tarik a fait sa thèse dans l'équipe de Jean Daliba. Et il est ensuite parti en postdoc au MIT, dans l'équipe de Martin Sverlein. Puis, il a fait un autre postdoc à Munich, au Max Planck, avec Immanuel Bloch, dans lequel, en particulier, il a fait un très beau papier sur many body localization dans ces systèmes. Voilà, donc Tarik va nous parler de microscopie dans le continu, et je lui laisse la parole.
Okay. Merci beaucoup, Antoine, et merci encore une fois pour l'invitation. Okay, I will now switch to English. So, good morning, everyone. It is my great pleasure to be here to tell you about quantum gas microscopy of fermions in the continuum. So, let me start by telling you about the physics we're interested in. So, this is the physics of the BEC-BCS crossover in 3 dimensions and 2 dimensions. So, due to the limited time, I will only focus my introduction on the 3D case, and I will talk later on more about the 2D case. So, an important point here is that the space here is continuous, in the sense that it's not discretized as encountered, for instance, in optical lattices or in arrays of tweezers. Okay, so the system of interest here is a spin 1/2 system where we can tune, so 50% spin up, 50% spin down is the typical situation, and we can tune pretty much at will the attraction strength between a spin up and a spin down. In the limit of strong attraction, which I represent here, a spin up and a spin down form a dimer, a bosonic dimer, and if you take an ensemble of such dimers at sufficiently low temperature, they form a Bose-Einstein condensate. In the opposite limit here, spin up and spin down form weakly bound pairs, and if you have a Fermi C, they are very similar to the Cooper pairs of the celebrated BCS theory. So these 2 limiting cases that are just discussed, from the many-body perspective, they're not so interesting. They're well described by mean field theory, and things get more and more difficult and interesting as you move away from these 2 limiting cases. So now I would like to lift an ambiguity here, is that while here the attraction between spin up and spin down is strong, the interaction between dimers is repulsive. So this limit here corresponds to the weakly repulsive case, and this limit here corresponds to the weakly attractive case. So for those of you who are not used to this way of parametrizing interaction, here the interaction parameter is parametrized by 1/kFA. A is nothing else than the scattering length. This is the way we characterize typically interactions in cold atoms. Kf is the Fermi wave vector. So 1/kF is a measure of the interparticle spacing. So what you have here is nothing else than the ratio of the interparticle spacing within some factor over A. So you understand that as we move here, as we tend to 0 here, we enter the strongly interacting regime or strongly correlated regime. So this is one knob that we have in the lab, and we have 2 other knobs. We have the temperature, and we have the spin population. So this plane here is the plane of 50-50 population, like as much spin up and spin down. But this is something that we can tune here by moving along this axis, right? So note here that there is no tunneling, as opposed to the case of lattices. My temperature is normalized to the Fermi temperature, and here the interaction, the equivalent of the U/T here, so in the reverse, is what I have here, but I have no tunneling. Okay. All right, so this is the 3D phase diagram that we're interested in, because there are 3 axes. And a remarkable fact of the BC-BCS crossover, which was already mentioned today by Antoine, is that no matter the interaction strength, the system is superfluid at sufficient low temperature, no matter non-zero interaction strength. And hence the word BC-BCS crossover. Here, I presented this axis as a practicality, as an experimental practicality, but in fact, if I put it in a more formal way, and I write here the difference of chemical potential of the spin-up population minus the spin-down population, and I normalize this, and then you realize that here I have the effective Zeeman field, right? So this axis is actually very interesting because it allows you to explore the competition between pairing and Zeeman energy. All right, so the field is not new, and over the past 20 years and a little more, actually, we have learned a lot about the physics of this system. We know a lot about what happens in this plane here, the t=0 plane, and we know a lot about what happens here where the interactions are the strongest, right, at finite temperature. So this was the result of a lot of experimental work, and I here put some of the main experimental groups that contributed to this, with MIT, Gila, Innsbruck having started this in particular, leading the way. So there's also a very long list of theoreticians that I didn't have, they would have deserved to all be here, but they would have covered my slides, so I have decided not to put them. But I would like to emphasize that the BC-BCS crossover has really been a success story in the way experimentalists and theoreticians worked hand in hand together. Okay, so now this is what we have largely been exploring, but as you see, there's a lot of space left on this 3D phase diagram. For instance, the finite temperature plane here. For instance, if you look at this TC line, which is the transition temperature from the normal to the superfluid state, it has not been measured. It is only known here. It has been measured at MIT, and I think it's still also debated. There's no consensus, as far as I know, from the theoretical perspective. So this is still a cartoon, and it would be interesting to measure this. Of course, we would be interested in moving along this direction here, in this green plane. So, as I mentioned already, there is interesting questions related to the competition between pairing and Zeeman energy. And for instance, one could hope to observe an FFLO phase in this direction. All right, but even without looking into these regions of the phase diagram which have not been explored, if I only focus on the regions which have been largely explored, we don't know everything. I can tell you how the pressure depends on the chemical potential and the temperature or the density. In other words, I can give you the equation of state. I can give you transport coefficient, diffusion coefficient if you want, but we know very little about the microscopics. And this is the take-home message of this first part of the introduction. We know a lot about the global thermodynamic transport properties, but we know very little about the microscopics. And I'm not saying that nothing has been done. I'm just saying that the knowledge is limited at this stage. And this is true for the 3D BC-BCS crossover as well as the 2D BC-BCS crossover. So now, why is this the case? Well, this is the case mostly because of the way we have been probing the system. What we have been doing so far is using absorption imaging. So the way it works is very simple. So you have a cloud here, so this is a cartoon. You send a resonant laser beam, and you project the shadow on a CCT camera. And the distribution of missing photons on your image gives you a density profile. Now, you can quite immediately see what the issue can be. Okay, before mentioning the issue, with such density profiles, when it comes to measuring thermodynamics or transport, you have everything you need. But if you're interested to see what happens at the scale of the interparticle spacing or below the interparticle spacing, then you are easily in trouble. So for instance, if you look at the pixel here, first, if you are in 3D, there's an integration effect. So what you have here is an integrated density. Second, let's assume you don't have this 3D integration, either because you can slice the cloud or because you're 2D. Well, for signal-to-noise reasons, constraints set by absorption imaging, you cannot afford having less than a few tens of atoms within a pixel. So you are not in a situation to resolve the particles. Okay, so there's a limit to this argument. So you can play tricks or actually use physics to still access short-range physics, but I distinguish short-range physics from just microscopics. I would consider that short-range physics is included in the microscopics, but what we want here is really resolving the system below the interparticle spacing or observe phenomena that occur at this length scale. All right, so, there is an easy call of what would be an alternative probing method, which is quantum gas microscopy. So Antoine has introduced this just today, so this is perfect for those who were here this morning. So quantum gas microscopy was introduced in the context of lattice physics, in particular Hubbard physics. And so it was first used with bosons, so in 2010, and then with fermions. So actually many of these images correspond to the list that Antoine has shown this morning. So just as a disclaimer here, when we mention bosonic quantum gas microscope or fermionic quantum gas microscope, the quantum statistics does not play any role. It's just the choice of isotopes were such that the first isotopes on which cooling was done were bosonic, and then later on fermionic isotopes were imaged that way. But the quantum statistics really doesn't play any role. So recently, I'm not repeating what Antoine said here, but you understand that every single of these bright point here, so there's a different set of color mice, but every single bright point here signals the presence of a single atom. So in some cases, the atoms are not well resolved, but you can simply deconvolute your image and still access the microscopic properties of your system. Yeah, so there are recent interesting developments, so the imaging techniques are still going forward. So recently there has been quantum gas microscopy of inner triangular lattice at the University of Virginia in the group of Peter Schaus, who's now in Hamburg, and also for alkaline earth atoms in the group of Laetitia Taruel at ICFO, so here for the bosonic case. All right, so all this to say that there is this tool, which clearly is impressive, very powerful, as we saw today in Antoine's course, and what we want to ask ourselves is why don't we just import that to the realm of the continuum? But before getting there, let me tell you a little more words of how this works. So you typically have atoms in an optical lattice. So this is when you do lattice physics. You increase suddenly the intensity of the lattice to pin the atom, and you shine on what I call a clever light. This clever light is a cooling light, which has two purposes. First, to make sure that the atoms stay at the bottom of the well, and second, to collect fluorescence light that come out of the cooling process itself. Okay, so there's this dual purpose. All right, so now we want to apply this to the continuum. So the idea is fairly simple. So now again, there's no lattice. We have atoms which are either in a shallow harmonic trap or in a box potential. And to image, what we do is very simple. We shine on a lattice, we shine on the clever light that I just mentioned, and we can simply detect the atoms. So there's a special case here where I have put two atoms, on the same side. So here what happens is that you have what we call light-assisted collisions. The two atoms acquire sufficient energy, and they are lost in the system. So we refer to this as parity projection. It is not specific to the continuum quantum gas microscopy. It's always the case when you do quantum gas microscopy, and actually Antoine mentioned this this morning. Okay, so I made this sound very simple. In practice, to import quantum gas microscopy from lattice to continuum, there is a series of challenges that you have to tackle. Unfortunately, due to time, I will not be able to tell you about it today. But we have tackled every of these challenges through a series of papers which are here, and feel free to check out the papers or ask me if you have any questions. And now this continuum quantum gas microscopy has been applied in two groups at MIT. I will nevertheless tell you a little bit about this to give you a sense of the abilities we have with this setup. Okay, so I'm done with my introduction, and here's the outline of my talk. I will tell you first about the experiment, then about microscopy of Fermi gas, of an ideal Fermi gas in continuous space, and then about spatial correlations in a strongly interacting 2D Fermi gas. So the three parts, as we move away, so the parts are increasing in time and increasing in complexity, so hopefully everyone will be able to follow. So let me start with an overview of an experiment. So first, this is a lab, so this is how it looks. So here's our control room with all the computers where we prepare the sequences. Then the cables are sent to the main experiment that you can see through the window. Here's a closer view on the experiment. At the back here, you have a laser table where we prepare all the lasers that we then bring in, for laser cooling and imaging, which we then bring into this main table here via optical fibers. So for those of you who are curious and have never seen one, here's how it looks like for the laser table. So usually I don't have a picture for the inside of this experiment here simply because, usually it doesn't work very well. So instead I have a CAD to give you an overview of how it looks like. So this is a vacuum system. Here we have an oven where we have put a chunk of lithium-6, which is a fermionic atom. We're going to heat this up at 800 Kelvin, which will create a stream of atom coming my way. And we're going to slow this down using a laser beam, also with the help of these coils here. We're then going to apply magnet-optical trap. So this is a standard cooling technique, which brings the temperature of the atoms to 1 millikelvin. So we lost 6 orders of magnitude in a few seconds, even less actually. And then we're going to cool down the atoms to even lower temperature at 50 microkelvin, and then load them in an optical dipole trap, which is a tweezer, which has the form of a tweezer, of a wide tweezer, and then transport the atoms to the sign cell. And once we are in the sign cell, we evaporate the cloud and create a given state of matter. It can be superfluid, it can be anything. But the important thing is that this is where we want to perform quantum gas microscopy. So now to perform quantum gas microscopy, you need 3 ingredients. You need an optical lattice. In our case, it is triangular. We can discuss why later. You need the clever light that I just mentioned. And you need a good camera and a high-resolution objective. So there is some impressive records of high NA objectives. In our case, it's just a good objective, 0.55, and we're happy with it. Okay, so here's a CAD of how it looks like in practice. So this is the glass cell. So this is where we usually trap our atoms. So here you see the arms of the lattice. So this is a triangular lattice, as I mentioned. You have a top view here. So a beam comes here and reflects out of this mirror. We call this a bow tie configuration. So you have the interference of this K vector with this one and this one, which are at 120 degrees, which leads to a triangular lattice for the polarization that for the electric polarization that we have picked. In the vertical direction, the atoms are confined in 2 dimensions thanks to a light sheet, which is here, which is a highly oblate trap. And we image the atoms which are now here via this objective. This is where we collect this clever light that I mentioned. And the clever light is what we call Raman sideband cooling in our case, and you have the geometry here. So this is for the expert. All right, so once we do this, we put all this together in the lab. Here's what we get. So on this image, every point that you see signals the presence of one single lithium-6 atom. You can zoom in here and extract what we call the point spread function, which is the response of your objective here, which is about 1 micron, and which is about what we want. We're happy with this. You could do better, but we're happy with this. And here, to give you a sense of how dilute we are, and diluteness will be very important throughout the talk. It's generally important if you want to do quantum gas microscopy. I'm going to zoom here and show you the underlying lattice. Okay, so now every white dot that you see here represents the well of a lattice. And you see that we have, on average, many sites between 2 atoms. And this will be important when you will want to have resolution on measuring correlation functions. So this is a classical gas, but as we'll see later, we have the same level of diluteness in the degenerate regime. All right, so this was the first part. We have a quantum gas microscope. Now, I want to make sure that this quantum gas microscope, when applied to a system in continuous space, works, doesn't introduce any bias. So for this, I would like to first apply it on a system which is, on the one hand, many-body, and on the other hand, benchmarkable. And an ideal candidate for that, and a great candidate for that, is the ideal Fermi gas in 2D. So here the 2D is just for practicality. The objective has a finite depth of focus, so we like to work in 2D. But it could also work in 3D. So now the ideal Fermi gas is a many-body system. To convince yourself at T equals 0, it's a Slater determinant. So it's unlike the situation of bosons where n bosons collapse, end up in the same wave function. But more importantly, we can compute everything, and by everything here, I mean all correlation function. And I'm interested in that because the correlation functions are what encode the collective information from my perspective. So the question is, when I image such a system under my microscope, do I recover the collective information? All right, so let's rehearse what we know about fermions. Well, they're governed by Pauli exclusion principle. So this is the classical cartoon. Now we can talk about the equivalent in position space. So if I have a fermion in R1, Pauli exclusion principle tells you that the second fermion cannot come at R1. This is very well encoded in the G2 correlation function, density-density correlation function, which can be computed exactly. Right? So this is the T equals 0 prediction for G2. And you see that G2 has much more information that just Pauli exclusion principle. It doesn't not only tell you that if you're on R1, you cannot come on R1, it also tells you with which probability you can approach this other identical fermion. And this is something which depends on temperature. And I show you here G2 as a function of T over Tf for a range of temperature. Okay, so it's something that we know and that we can compute. We can also look at G3 here. The idea is that you put one fermion here and one fermion here. What's the probability to bring a third one close to these two fermions? There again, you can compute the result at finite temperature. So let's put this in a checklist. So I have prepared a checklist here to make sure that I'm happy with my quantum gas microscope. And let's see if we can see G2, G3, and with which precision. Another property of the ideal Fermi gas is that it obeys Wick's theorem. So the Wick theorem applies to any quadratic Hamiltonian. It basically tells you that if you give me G1, the first order correlation function, which are right here, I can give you any higher order correlation function, G2, G3, etc. And just by some combinatorics, you can show that G2 is 1 minus G1 squared, and that G3 can be written as a function of G1 as shown here. Okay, and by the way, since the relation between G1 and G2 is very simple, I might as well have said that if I'm given G1 or G2, I can get any higher order correlation function. So let me add Wick decomposition in my checklist and see if this is something that we can verify in the lab. All right, so when we take an image, this is how it looks like. So now I switched color map from red on black background to blue, because now this is a cold cloud. And something that is important is that although we're typically interested in homogeneous properties, meaning in the properties of the homogeneous case, Fermi gas, interacting Fermi gas, very often we work in a shallow harmonic trap, which is not a problem because there's the LDA, which was mentioned already in the previous courses by Antoine. And the idea is that if you zoom in a central region of the cloud where the density is essentially homogeneous, you can consider this system as a homogeneous system. And in many cases, it's actually an advantage. This is an asset, because in one shot, you actually have a collection of homogeneous cloud with a varying chemical potential. Anyway, for this specific case, I have my ideal Fermi gas. I'm going to zoom at the center and let me measure G2, right? This is what's on my checklist. So I'm going to take one atom at the center and ask the question, at a given distance, what's the probability to find another atom? And at the largest distance, et cetera, et cetera. And I repeat the process through every single of these atoms and over 2,500 images. And when I do that, here's what I get. So here's G2 as a function of KFR. The data is these markers here. This thick line here is the t equals 0 prediction. And here, the line that you see is a fit, which gives us the temperature. And you see here that we extract a temperature of 9 nanokelvin and correspond to T over TF of 0.47, which is in the degenerate regime. We have much colder clouds, but it was interesting here to show you a case at a finite temperature and to deviate from here. Okay, so something important that I forgot to mention, sorry, here, so there's only one fitting parameter, right? From the image, we have access to the density. Density gives us Kf and gives us Tf, so there's only one fitting parameter, which is temperature, which is always nice to have when you have such a nonlinear function. All right, so now we can do the same thing, but not with one point, but with pair of points. So I'm going to fix the position of one point and another, and look at the probabilities to find a third one. So I can look here, here, etc. And when I do this over all the possible pairs, and through averaging over 2,500 images, here's what I get. So now this is G3, so I need to have a 2D plot. So just to help you reading it, so I have this density plot. So where 0 is the white corresponds to 0, and this tone of blue here corresponds to 1. And what you see here, the white dots here, no, they're not white dots, the white disks here are nothing else than the Fermi hole surrounding each member of the pair, okay? So I have two pairs, atom 1, atom 2, and I look at the third atom around, and then I look at two pairs closer and two pairs closer. So this is what I'm doing here, okay? And an interesting observation is that you see that here it's getting fainter. So it's not a problem of signal to noise. This is simply Pauli exclusion at play, right? So if I'm bringing two fermions close to each other, the probability to have a third one even closer is extremely small. So it's actually a nice visualization of this effect. Okay, so now if we are true to ourselves, we never really like density plots as physicists. So I'm going to take cuts through these in order to have some more readability and read the contrast. So here again, the markers are the data. And you see how the two Fermi holes are merging as we come here. And the solid line that you see, so there's a solid line which is hidden behind the marker, is not a fit. This is actually the theory prediction using the temperature that we extracted from G2. So this shows you that G2 and G3 are consistent to a high degree. And this makes you very happy in terms of imaging. But now you might say, okay, well, if you want to compare whether G2 and G3 are consistent, you might as well use Wick's theorem, right? You take the G2, you apply Wick theorem, and you see whether you fall on the same data point. So this is what we do, and here's what we get. So now there's no fitting whatsoever. The blue is the direct G2 measured from the images. G2 is using Wick's theorem. And with this, we have completed our checklist, and we can conclude that we performed reliable quantum gas microscopy of a many-body wave function in continuous space. So the paper is here. This is not the title of the paper, but the paper is here if you want to check it out. All right. So now let's move on to the interacting case. So far the physics that I put in here was simply Pauli exclusion principle. Now I'm going to add two ingredients, and we are back to my introduction. I'm going to put attraction, but two-body attraction, which can only happen between spin-up and spin-down. This is something that Antoine already mentioned, because these are contact interactions. And I'm going to add tunability, also something that Antoine has mentioned via Feshbach resonance, right? Okay, so with this you get in 2D now, a phase diagram which looks like this. So this is the equal spin population plane, right, which is the equivalent to the, this plane in the 3D case in my introduction. Vertical axis is still temperature, normalized to TF, and here the interaction parameter is not 1 over KFA anymore, it's log of KFA. Why? Because we're in 2D, and in 2D there is always a log. So here's the BEC side, here's the BCS side. And here again, the interesting regime is when the amplitude of the log is smaller than 1. Like, okay, so this is the interesting regime. So we have taken data which in this region, right, at rather low temperature, so absolute temperature is on the order of 3 to 6 nanokelvin. And reduced temperature is below 0.1. So for reference, 0.1 is roughly where the normal to superfluid transition is expected. So the large majority of the samples I'm going to tell you about here in the superfluid regime, but we can talk about it later. All right, so when we take an image, here's what we get. So here again, I change color map. I'm purple. I was blue before. Why? It's because I'm only imaging the charge, right? I'm not spin resolved at this stage, right? Ideally, you might think that if you want to study the BC-BCS crossover, you want to have a spin-resolved imaging, where in one image you know exactly which one is spin up and which is spin down, and have a red and blue image, right? So it turns out that's something that we have in the lab. Actually, we're setting it up in the lab to be more precise. But at first, we thought that maybe there's still a lot we can extract with this. So first, as a reminder, again, we're in a shallow harmonic trap. And just by analogy to condensed matter here, this imaging, I will call it charge imaging. I don't know if I'm spin up and spin down. It's simply the total density. So I will call this charge imaging. This is an image of a weakly attractive gas. And now let's just see what happens if we increase attraction. When we increase attraction, here's what we see. Okay, let me do it again. Okay, let me do it a third time. Okay, so you see that you go from a situation where you have individual blobs to a situation where the atoms organize in pairs. Okay, and when we saw this, we said, okay, let's just keep working with this. Maybe there's interesting things to see. Now, if you squint your eyes, not if you squint your eyes, but if you pay attention, the number of atoms has reduced. Why is the case? It's because of this Doblon losses. So you have an average size of the pair for a given value of log of KFA or A2D. Sometimes they're going to fall up on the same site and you lose them. This is what happens here, right? So you might think, so much for being dilute, because being dilute allowed you to avoid this situation, which I didn't have before, and now we're back in trouble. But as you will see later, actually, it's actually an asset, and we're happy to have these losses. Okay, so now one more point is that, as mentioned in one of the experiments today, we can also get rid of one spin state. So for instance, here's my charge imaging on the right. But I can also push away spin down and take image spin up, and push away the blue spin and be only left with the red spin. So I have all this information, and as we'll see actually with all this information, there's a lot we can do. All right, but just like in the previous case, let's rehearse our correlation function, or let's try to see what we can expect. So there's 3 types of correlations you can be interested in. Equal spin correlation, and we're back to the Fermi hole story. So in the presence of interaction, this Fermi hole might change due to the effect of interaction, but let's see. You have interspin interaction, which is really what you're interested in. This is what measures pairing. So we don't know a lot about this. What you know is that it's going to be normalized at long distance, so it's going to go to 1. And at short distance, by analyzing the short-range behavior, you know that there is a divergence. Actually, you can show that G up-down, when R tends to 0, scales like log square of RA, which is diverging here, okay? Again, we have a log square this time. This quantity here is what we call the contact, which is important in the context of cold atoms. Here in between, we don't quite know what happens. Okay, now the third correlation function that you can think of is the charge correlation. So if you prefer total density correlation, but next to condensed matter, I'm going to call it charge, and this is my purple color. If you remember, this is exactly what I have access to in my purple image. Now, if you want to have an idea of how it looks like, well, you can just decompose your charge correlation. So purple and purple can be decomposed into 4 correlations: up, up, down, down, up, down, and down, up. And in the case of a balanced system, as much spin up and spin down, these 2 are identical, and these 2 are identical. So you can write this result, right? GNN is 1/2 of G up, up, could have been G down, down, plus 1/2 of G up, down, could have been G down, up. So, here's my relation. So from this, so you remember G up, up is a Fermi hole. So now you're going to have to take half of this. So it's going to give you this. And then you have the divergence. So you expect the charge correlation to look like this. So it starts at 1. And then you have a dip because the Fermi hole is pulling you down. And then you have this divergence at short distance. So you can expect curves like that. Okay, let me summarize. We have 3 interesting correlations that we can, like natural correlations that we can look at: equal spin correlation, interspin correlation, charge correlation. These ones I can get directly from my blue images or my red images, but I like blue. The charge correlation can be extracted directly from my purple images, where I have everything. Here, this is what you would extract directly if you had this spin-resolved imaging that we don't have yet, right? Where in one image you see the red and the blues, right? But it's not a problem because I have this, and I can just use my formula. All right, so let's see what we can get with this. So we are more interested in the fermionic side. So we're going to take data here from the far BCS side to around 0. So here I'm on the fermionic side, okay? And we take an anchor here, hoping to connect to BCS theory. And we take mostly points here in the crossover, which is the interesting regime. All right, so when we do this, here's what we get. So here's GNN, and here's the first value of GNN for the BCS case. And then we're going to move towards the crossover. And as we do this, here's what we get. Nice. And then from this, we can get the G up down, because I also, for every of these interaction parameters, I also have the same spin images. And here's what we get. So, well, you might say, you increase attraction, you see pairing. This is obvious. Well, yet, this is the first direct observation of pairing in situ. As far I'm aware of. And note here that it goes quite far, because if you had bosons, for instance, you would go to 2. So the increase here is quite remarkable. All right, so now let's look more into it, and let's zoom. There's actually things happening here, and actually there's. Let's see what we can see. All right, so here's now 3 rows. First row corresponds to up, up. You have down, down. Here's an inset. Here you have the charge. And here you have the G up, down. So this and this are zooms right in this little lower part of the correlation function. So there's a lot to unpack here. And unfortunately, I don't have time to discuss everything. But this slide could take me just 15 minutes. So I will just focus on one point, which is what happens for the G up, down. So again, the markers are the data, and what you see here, the solid line, is BCS theory, okay? 2 points. What you look first, so what surprised at first is that, you remember, but we took this point because we wanted an anchor. We wanted to make sure that when we are on the BCS side, we recover BCS theory. Turns out that we don't. What BCS theory predicts is an uncorrelated gas. G uptown is equal to 1. Okay. So I'm a bit extremist here. Truth is that there's a small divergence, but at very short distance. But it is essentially an uncorrelated gas. So it's quite remarkable. It was a surprise to us. At log KFA equal 8, the BCS theory fails. And then we move towards the crossover, and log KFA equal 4. BCS theory still have a hard time catching up. And then you might think, okay, I'm not showing everything. You might think that there might be some agreement, but it's actually fortuitous. It is fortuitous because you see that in the data, there is a dip that appears here. It turns out this dip appears in a region which is forbidden by BCS theory. So this purple area here is forbidden by BCS theory because BCS theory tells you that G up down cannot go below 1, right? The reason is G up down is 1 plus a constant times absolute square of something which is like a Bessel function. So what we see here is not a deviation to BCS theory. We see a fundamental violation of BCS theory. So of course we asked around if people if they were aware about this, and at some point we had no choice but to ask our friends who do AFQMC Monte Carlo, and here's what we get. Again, look, focus here, and now I'm comparing to the AFQMC, right? So here you see that the AFQMC agrees really well in the BCS side, right? Remember that BCS theory was just flat. And AFQMC calculation do show the existence of this dip. So this dip exists, and we're still trying to figure out what's the physical origin of this dip. We might have some ideas, but it's too preliminary at this stage. So there's some deviation which appear here, which we understand, but this is not a big deal at this stage. So we see a dip, and this dip is actually confirmed in the AFQMC calculation. This is the main take-home message. All right, so here, let's keep going. Just like before, we can measure G2, we can also measure G3. Turns out that for G3, the community historically was always stuck when they didn't have this spin-resolved imaging, right? Because it's related to the amount of information you have. So here, you have 3 correlations, and I have 2 images. Well, okay, I have 3 images, but up, and down are the same. My red and blue contain the same information. So I have 2 types of images with 2 distinct information. The charge images and the single spin images. So I can get the third one. But now if you want to look at higher order correlation, if you don't have spin resolved, you're stuck, right? Because clearly here, if you look at GNN with 3 purple, okay, the decomposition is here. Now you have 8 terms. These 2 are identical, but in general, those are not. So you don't have enough images to resolve this. Except if you look on equilateral triangle. Now, if you look on equilateral triangle, all these 3 correlations, those at the bottom, the 6 correlations that are at the bottom, are now identical, right? Which is one of the advantages of the triangular lattice, by the way, if you want to look at short distance. So now you can have again an equation with, 3 unknowns and 2 input, okay, which is here. And by the way, I should give credit to Maxime and Cyprien, who are in the audience, who came up with the idea of using equilateral triangles. Okay, now again, I don't have time to discuss everything. I'd like to focus on something else. I would like to focus on something specific than the direct comparison to the theory. So here the markers are the data. So again, the first row is single spin. Second row is charge, this is the purple color, and this is the interspin, right? And they only have 1 interspin because you can change this up-down, okay? So the markers is the data, and I only want you to focus on the shaded area. The shaded area is a Wick relation, right? So, of course, when you go to in the ideal Fermi gas, we verified that Wick worked because the Hamiltonian is quadratic. Now, when we put interactions, the Hamiltonian is not quadratic, especially because you have an interaction term, especially in the crossover. But if you look at here, so don't compare to theory, just compare to data. So this is a direct measurement of G3 are the markers. The shaded area is the G3 obtained via Wick relation, and it just works really well. And we're still a bit surprised about that, but we might have some insight. So there again, so does it mean that there is no new information in a 3-point correlation? Well, it seems to be the case. Now, just let me be specific. I'm not saying that the Wick theorem is valid for the BC-BCS crossover. What I'm saying is that the relation between G2 and G3 is valid. And in fact, with the help of our colleagues who do the FMC calculation, who have access to G1, we don't, we have been able to verify the following. If you look at the Wick relation of the type G2 as a function of G1, it fails. If you look at the Wick relation of the type G3 as a function of G1, it fails. But now if you take G2 as a function of G1 and plug it here, you obtain a relation between G3 and G2, and it holds, which is quite remarkable. This is exactly what we see experimentally for the whole BCS side. So for now, it's only for equilateral triangle, but we think that actually that it might be more general than that, and I'm happy to discuss it. All right, let me see how much time I have left. Okay, almost done. All right, so now let me move to the contact, and we move to the contact mostly because, you know, it's a quantity that people are interested in the community. So here's again the expression, I mentioned it already. And how can we measure the contact in our case? Well, you can do something very simple. You just count the number of atoms you typically have on an image. And here, actually, it's in the central region of your image. So here's an histogram of the number of atoms, so just a probability, you know, and just a histogram. So on your blue images, here's the number of atoms that we get in a certain region at the center. Behind the blue, you have the number of red atoms that we find, and you see that we are quite well balanced. And if you didn't have the losses, you expect that when you look at the charge images, your histogram would be centered around this black curve here. This is n bar up and down, n bar down. But in practice, we see that it shifted to the left. Well, because you have losses. So this is for a strongly interacting regime, where the strongly attractive regime where the pairs are close. And here we're moving towards the BCS side now. So, and you see that the shift is smaller and smaller. So you are now in a situation where you thought you had an issue because you had losses. The losses now give you exactly the contact, right? The contact is a short-range behavior of up-down, right? What's the probability to find two atoms within a small volumes when R tends to 0? This is directly in the losses. Okay, so what we thought was an issue is actually an asset here. But still, we can only do that because we are very dilute. We can only do that because the probability to have 3 atoms on the same site is extremely weak. Okay. Okay, so from this we can extract directly the contact. So here's what we expect. So this is the AFQMC calculation from previous work here from Shiwei and his colleagues. Here there is the BCS mean field theory, which is this dashed gray line here, and the Fermi liquid, which comes from the tail. So it's more practical to look at it at log scale here. Well, there's different kind of information. So here's the same thing in log scale. So you see here the BCS mean field result, which is nothing else than the energy of the dimer. Here you have a Fermi liquid result, and you see that the AFQMC connects this very well. Now when we analyze our data and extract the contact, here's what we get without any single fitting parameter. Okay, so what we have learned is the following. We have learned, which was a surprise to us, that BCS theory fails in the weakly interacting regime already at log KFA equal 8, right? Which I think is a surprise. We found that the pair correlation, G up-down, violates a fundamental constraint of BCS theory. G up-down can have values below 1. Is this a general signature of strong correlation? What we know for sure is that this is forbidden by Wick theorem. When I say that it's forbidden by BCS theory, it's BCS theory plus Wick, but you expect Wick to work because Hamiltonian is quadratic in quasi-particles. Other important point, what we discovered is that 3-point correlation do not contain additional information with respect to 2-point correlation. And there is a Wick-like relation between the two. So there is 2 information here. Already, it's one big news that for me at least, that 3-point correlation do not contain any additional information than the G2 correlation, like second-order correlation. But it's also remarkable that this relation is of the Wick type. Okay, at least for me. Okay, is there 3-body physics in the system at all? So this is something that we're exploring with Shiwei and his colleagues. Okay, and finally, we see that the spatial form of correlation is really an excellent observable to distinguish between theories. Now, one last point that I didn't have to discuss, and maybe Shiwei will talk about it this afternoon, is that now, if you look at each spin component in an interacting Fermi gas, and you look like at G up, it is undistinguishable from the one of the ideal Fermi gas. So I repeat this, throughout the crossover up to, as long as you're on the fermionic side, if you look at G up or G down, it is undistinguishable from the one of the ideal Fermi gas. So the system organizes itself in this remarkable manner where this guy is happy, is ideal, so you start from non-interacting, you turn on interaction, right? So this guy, among its partners, like its pairs, pairs, well, wrong word, up alone, doesn't see anything in terms of changing for him in terms of correlation. Down alone doesn't change anything in terms of two-point correlation, but they still pair with each other. So now when you observe that, it might be less surprising that there is no additional information in the three-point correlation, but at this stage it's something that we're still exploring. Okay, so with this, I have showed you what we think is an almost complete study of microscopic behavior of a strongly interacting Fermi gas, and the paper has recently been put on the archive. All right, so to summarize, so we have 4 works on quantum gas microscopy in the Continuum. I didn't have the time to discuss all the aspects of each of these works, but just some facets of it. So today I've shown you that we have a quantum gas microscope that works, that we can study correlations in an ideal Fermi gas, which for us serves as a benchmark that we're doing the right thing, and then being confident that we have a reliable imaging, we have been able to observe correlations, spin correlation, charge correlation, second order, third order in a BC-BCS crossover, and observe phenomena which I think the community was not necessarily aware of. There's also a paper here on fluctuation, where we show how we can obtain very reliable thermometry in the system, which is in general an issue for these systems. So I would like to thank the people who did the work. Most of the building and development work was done by Joris, Maxime, and Tim. And before that, there's also Shiwei and Kulun, who played really an instrumental for the actual building part. And Cyprien really played the major role for all the interacting part. Bruno Potser also, of course, played a big role. He used to be a postdoc with us, and since we get along, we still collaborate. And of course, special thanks to Shiwei and Yuan Yao, who really did the AFQMC calculations, without which we would have not been able to have as much insight on what we're observing. So I hope that we're still able to continue this strong collaboration between theory and experiments on the BC-BCS crossover. And with this, I thank you for your attention.